Welcome to week 11 of building scalable distributed systems. And in this week's material, we're going to discuss serverless computing platforms. We'll first motivate why serverless computing platforms are attractive, and then give a fairly detailed overview of Google's offering, the Google App Engine, and show you some experimental results that show how GAE, Google App Engine, can be configured to provide performance and scalability to match the application needs. And we'll finally just do a quick coverage of Amazon Web Services Lambda, which is an equivalent service to Google App Engine. So first of all, why is serverless computing an attractive proposition? So if you think about the cloud-based services that you've been building in this course so far, you're connecting to them from your laptop over a network, and when you send requests in the last assignment, you were sending requests to a load balanced set of services, and these services were then communicating with other services. In your case, it's a database, but it's soon going to be more services. So essentially you are provisioning resources in the cloud and configuring them using load balancers and configuring their size of the instances and the networking configuration, etc., etc. So you control and administer the resources that you utilize within the cloud. So this is great. You get to choose the instance types you want. You can choose lightweight ones, which are cheaper, or you can choose more beefy, powerful ones, which give you more performance, but at higher costs. You get to install your own software. You can use anything you want. The VMs, the virtual machines, are just basically bare iron that you put on whatever software you like. You can do instance monitoring, so you can understand how they're performing, when they go down, when they don't, when they're alive. And you're responsible for ongoing maintenance. If an operating system version changes, then you have to do an update, or if a platform that you're using, such as Tomcat, has a new version or a security update, then you have to administer that site. And as the load grows, then you have to think more about how you configure your load balancing, and perhaps how you increase your database capacity so that it can handle the increased load. Maybe you scale out your database, or you scale up your database. You'll probably want monitoring in place so that you can understand the behavior of your system as the load grows, as it scales, and this will enable you to make decisions about the changes you may need to make to your configuration. And also, if you're experiencing spikes in performance, then you are responsible for configuring the system so that it scales down during low usage, and this of course saves you money, which is never bad. So in summary, when you deploy your application on virtual machines in a cloud-based system, you are responsible for the ongoing maintenance and monitoring and management of that system. You check it's alive, you restart things when they fail, you manage the performance and scalability through monitoring and feeding the monitoring data into your decision making. You're also responsible for system administration, because when versions change or you need to do updates to your core platforms, then it's your responsibility to make sure that those happen. And of course, there's always the potential for resources to be spawned in your cloud's administrative zone that you're not actually using. People may spawn machines and then just forget about them, and this incurs costs. And there's several horror stories of organizations incurring tens of thousands of dollars of additional cost from cloud-based resources that they'd provisioned but were not utilizing, just provisioned by accident. So again, that's another area of care that you're responsible for when you deploy your own systems on virtual machines in a cloud. Serverless computing differs from the model we've just described. It's also known as function as a service. Basically, you don't manage or provision or deploy your own virtual machines. The platform delivers computing capability for you. Basically, you just upload your code to the platform. You give it a set of configuration parameters that controls within certain bounds how that code will perform as requests arrive. And then the platform itself is responsible for invoking your code and running it without you having to do any administration of virtual machines. The beauty of this is typically on any serverless platform, if you're not running any requests, say you have a very spiky workload and during the nights there's just no requests coming in, then you don't pay anything. You don't need a virtual machine deployed that you're paying for. So serverless computing can be extremely useful for such workloads. And the platform is responsible for scaling up and down for you. You don't need to configure a load balancer. You just configure a few parameters and then the platform will deploy more computational resources as the load grows, and then pull back the computational resources it's deployed for you as the load diminishes. So potentially this diminishes your administration costs and the complexity of administration considerably. The three main commercial cloud platforms all have their own function as a service, serverless platform technology that you can utilize. They all work in a similar way, but similar but different, as all these things are across vendors. In essence, you just upload your code to the platform. You configure it using a set of configuration parameters which differ between platforms. So it's important that you understand what you're getting when you change these values. And then your code is triggered when an event occurs that you configure. Typically this is a HTTP request coming from the outside, but it can also be such an event from, say, a queue, in this case the AWS SQS queue, or an update to a file-based object, in this case the block storage based on S3 in AWS. So a trigger will invoke your function will execute under the control of the serverless platform, and all is good. Of course, there's trade-offs. Your code has to be stateless. Because the platform itself is invoking a new instance of your code to handle requests, there's no easy way to handle state in between invocations. So the platform ensures that your code has to be stateless to operate correctly. And if you do need to manage state, it has to be externalized in the places we've discussed so far, caches or persistent stores. Most of these platforms have a configurable execution duration for a request. As the slide says, it's typically of the order of 1 to 5 minutes. If by any chance your request needs to execute for longer than that, then it will not be suitable for this kind of platform, and the request will actually be killed. And so these sorts of platforms tend to be much more suitable for short-lived requests that are called on demand. And there's also things that you have to consider to do with startup latencies. If there's no instances of your code resident in the platform when a request arrives, the platform has to load the runtime for the code that you're using. So if it's a Java function that you've supplied to the platform, it needs to load a JVM into a computational instance within the platform and start the JVM and load your code, load your jars, etc. And then it can invoke the platform, the service itself. Most services have ways around this called warm starts, where you can keep certain elements deployed so that you don't pay for this cost of a first call. But again, this is all really application, language, and environment dependent, because some languages such as Golang, as we'll discuss soon, are much more lightweight than, say, Java or Python, so they have much lower startup costs. And of course, you pay differently on every platform, and this slide here gives you some comparison, which you can look at your leisure. But basically, you're paying per invocation. You also pay by the amount of memory that your machine uses, and typically when you deploy a service, you can say, I want to have this much memory available, and the cost is scaled by the amount of memory that you have. And so you have to think carefully about how much memory your service requires. And so again, study this at your leisure. You'll see different things are charged by different vendors. So here an API gateway is free, here it's not. You have to figure this out depending on the vendor that you choose. What's an API gateway? An API gateway is a very common component in services based on cloud-based systems, typically serverless-based systems. You can think of it as the same as a facade in an object-oriented program. The facade pattern basically offers an aggregated interface of all the underlying services, so that when clients make a call to the application that's running, the call to the gateway is then routed to the actual service, in this case the function as a service, which implements that function on the platform. So it's a level of indirection. It's almost like it behaves very similarly to a load balancer. You can also invoke certain functionality in API gateways. You can ensure that they can do authorization, authentication. You can do monitoring of performance. You can manage API versions, which is great as your application evolves, and you can do all sorts of clever things in some API gateways, like input validation and traffic management, etc. So they're powerful tools which need to be used wisely, because if you embed too much functionality in your API gateway, it can potentially become a bottleneck. So these again are provided by the cloud provider. Even though there are open source ones you can deploy, but you'd be responsible for deploying them yourself on virtual resources. So I said it basically behaves like a facade. The client connects to the API gateway, it can authenticate here, then it sends in the request, and the API gateway knows where the actual function lives, which implements the request from the client. The beauty of this again is it means you can move things around, so that the function behind here is not exposed to the client, so you don't get a direct coupling. And the API gateway, if the signature changes, the API gateway doesn't have to change. It can just basically do any mangling of the data or the formats to make sure the new function can be called. So you'll see API gateways very commonly in this kind of world. So without further ado, let's look at a specific platform, the Google App Engine. So Google App Engine is part of the Google Cloud Platform, and it's been in full release for the best part of a decade, and longer actually, since it was originally in preview, I think in 2008. When you use Google App Engine, you can deploy an application that comprises one or more services. It's your choice what languages the services are written in. They can all be in the same, or they can all be in different languages, the languages that are supported by Google App Engine. We'll talk about that in a second. And you can configure each service differently, so that they can be, say, more or less responsive to requests and have more memory and computational power allocated to them. Services can also have multiple versions, and each version can have multiple instances that handle requests. So if that's a bit confusing, hopefully this slide makes it a little bit clearer. An application has a number of services. The services are the things that clients will call, so they expose an interface. Behind each service there can potentially be different versions that implement that service, and different versions can have different instances that implement that functionality too. So why would you want different instances? Well, basically what you can deploy using Google App Engine is equivalent to deploying your own microservice. You have your source code, it provides an API, it can be configured, it can have a database that it calls behind the services, and you can version it. You can version different instances of the API. Instances are really useful because you can use a function of Google App Engine called traffic splitting to send part of the traffic that comes to a particular service to different instances. So A/B testing is a very common technique whereby you can deploy two different versions of the same behavior and then compare how they behave based on requests from live traffic. So Google App Engine's traffic splitting will enable us to deploy two or more versions of the same service, and then we can see maybe which is cheaper, which performs fastest. Maybe one implements a different version of the UI, and we can see if people prefer that version of the UI. So A/B testing is great for testing hypotheses live on a system. And so that's basically what you can do with traffic splitting and all this versioning and instances. So instances are the things which are managed by Google App Engine and can be auto-scaled. So as a request comes in, we'll look at this on the next slide, a request comes in for the instance, then Google App Engine will send a certain number of requests to a single instance. When that instance becomes busy, it increases the number of instances and starts sending new requests to the new instances. So this is the auto-scaling functionality. When you auto-scale, what GAE is actually doing is it's deploying a new instance of your runtime for the language that your service is written in. So if you've written in Java, it deploys a new JVM onto the GAE platform, starts the JVM, loads your code, and calls your API. If it's Python, it loads the Python virtual machine. If it's Golang, it loads the Golang runtime. And because of this, a new instance has a startup cost. If the instance is already resident and it has some capacity to be called, then we can just reuse an existing instance. But if we need to create new instances because there's too many requests for a single instance to handle, then we have to pay these startup costs, and they vary from language to language. You can configure for each instance a minimum and maximum number of instances. Your minimum can be 0, or maybe you just want one instance deployed constantly, so you get around initial cold start costs. And maybe you want to say, I don't want to pay for more than 20 instances to be loaded at any one time. Maybe that should be enough to handle any capacity that I need. And if I get swamped, then I can revisit that decision later on. Unused instances, so as I scale up and then instances are not used because the request load comes down, unused instances are removed automatically by GAE, but you basically pay by the 15-minute interval. So whenever you load an instance, you're paying for a minimum of 15 minutes. And so it's not free, but it's 15 minutes isn't too bad, and costs are pretty cheap. And you can configure instances based on the number of CPUs and memory usage. So of course you pay more for the more powerful instances that you utilize, and you can configure that when you deploy your service. So here's just a depiction of it. We see requests coming in, they enter the GAE platform, and there's a load balancing functionality which is part of GAE. It interprets a set of configuration parameters that you provide, we'll talk about very shortly, and as requests come in, it will manage the amount of instances that are deployed. As requests grow, more of these will be deployed by GAE, and as requests diminish, then these will be relieved and you'll stop paying for them. You can also have idle instances, so if there's nothing happening, no requests coming in, then an idle instance is there ready to be called whenever a request comes. So and you can configure GAE so it always has an idle instance available, basically a warm start. So this is the kind of functionality that GAE provides for you. So let's look at how this auto-scaling stuff works. When you upload your code to GAE to create an instance, you also provide an app.yaml file, which has a number of parameters. Let's just look at some of these. So by default, when GAE is running your code on a CPU, when the CPU reaches 60% utilization, then a new instance is created. The service is scaled, new instance is created. Also, when an instance has 10 concurrent requests, by default, if an 11th one arrives, the service is scaled. So these two obviously interplay with each other. in a subtle way. Actually, it's a little bit more complicated because by default, the number of instances is only 6, as there's another setting called the target throughput utilization, which by default is 0.6, and that's 0.6 of 10. So by default, when you get more than 6 requests on an instance, or the CPU utilization goes above 60, then a new instance is created. You can also specify the maximum and minimum wait times in the queue, which is managed by the Google App Engine load balancer, that requests should wait before new instances are created. So basically, if requests in the queue are waiting longer than 30 milliseconds, then GAE will start creating new instances to try and reduce this value, the average time that a request waits in the queue, to less than 30. And you can configure these values, and they're subtle interplays between the two, which we won't really go into. Main thing to realize is this is pretty complicated. All of these parameters are codependent. When you change one, the value that another one has will affect the overall behavior of the system. So configuring these types of services to achieve excellent performance, scalability, and not costing you too much money is a tricky exercise. So let's just try and explore this problem a little bit with some concrete examples which we built on Google App Engine a year or so ago, and have given us some quite revealing results. So the overall aim of our experiments was to understand how effectively Google App Engine scales up and scales down instances for a given application. So here you can see this is actually a load test that we ran on our code, and I'll talk a little bit more about what the code does in a second. So this is what the client sees when it scales up the number of requests from 64 to 1,024 clients over the duration of 400 seconds here this test took to run. So first of all, when we have a low number of clients, then GAE starts up and then reaches a nice stable level of performance about here of about 500 requests per second. Then suddenly our client will scale up once the initial phase of the test is completed, and the number of requests grows to, I think it was 512 clients here. So the number of requests grows significantly, and GAE nicely scales up here. It handles the increase in load, and it plateaus quite nicely. And then after a certain amount of requests has been sent by those clients, we scale up the load to 1,024 concurrent clients, or blasting, in this case, post requests. So we're invoking writes on the database behind the scenes. And here you can see GAE again scales really nicely. The throughput grows really rapidly from 3,500 to 4,000 requests a second to averaging around 8,000. For a sustained period. So this is running for 260 seconds or so, over 4 minutes of sustained load. And GAE is pretty stable. There's a bit of jitter, but nothing significant. This is pretty good performance. Then towards the end we get a spike here because we start the next phase before this one's completely finished, so there's a little bit of a spike, but that's kind of just a test anomaly. And then we start running less clients back down to the level we had over here, and you can see GAE, the performance drops because there's less requests coming in, and it stabilizes, and then we scale down right to the end and run another phase with less clients, I think 64 clients here, until the test completes. So what we can do when we monitor this behavior is we can see not only the average latencies and the throughput that we're getting, the percentiles for each request, but we can also measure cost, and we can understand how the cost of running this test varies across different configurations for our application. So they're the 3 phases that we're really concerned about. So let's start really simple with our experiments. We're going to compare the cost of programming language and see if it has a significant effect on the performance an application has and the costs that it incurs. So we built an experiment. We built a pretty simple application. It has an API. The requests that we call were mostly writes. I think it's about 80% write, if I remember correctly, post requests, and about 20% get requests. So we wrote the same application logic supporting the same API, but we wrote it in 4 different languages. So we used a Golang implementation, Java, Python, and Node.js, which are 4 platforms supported by Google App Engine. Behind the scenes, they all store and read data from the same database, a NoSQL database provided by a Google Cloud Platform called Google Data Store. And we configured them to have exactly the same hardware configuration. They're known as B1 instances. It's kind of like the free tier version of GAE. And we kept all of the order scaling parameters in app.yaml default. So we did no configuration of the actual auto scaling performance in this particular set of tests. And of course, we had exactly the same client running from exactly the same location, all the servers running in exactly the same data center, and executing exactly the same test load. So we kept all of these parameters stable and just varied the language that was executing. And we compared the performance. We captured latencies and did lots of calculations to calculate throughput, means, medians, and percentiles. So let's just have a look at what difference the programming language makes. Well, the first observation here is, as you can see, we scale up the requests from 128 clients to 1,024 clients. And the average for the whole test for all the phases is the blue bar, and the peak phase. So the peak phase is when there's just 1,000, the peak number of clients in each test, so 512 or 256 or 128, to see what the actual peak, sustained peak throughput was. And it should be higher than the overall test, because the overall test has phases when there's less requests coming in from a smaller number of clients. So you can see here, all of these languages have a really nice scaling curve. It's pretty impressive. So GAE is doing a great job in scaling our application as the load grows. So that's a really positive outcome. So you can see the peak loads are variable. So Go is performing much more impressively than Python. Python coming in at a peak of about 9,000 requests a second, whereas Go's way over 10,000. So there's variability here, and the language is obviously having an effect on performance. So let's compare just one test, the test with the most client threads, 1,024 concurrent threads, all spewing requests to the service as quickly as possible. This compares the languages. Again, it's the total throughput for the whole test and the peak phase only. And we can see Go is pretty fast compared to the others. The other 3, there's not a great deal of variability. Node a little bit higher than Java peak, but overall it's actually slightly less. That could just be test variability. There's a small percentage of error. All the tests were run multiple times on average, so we got some consistency across the performance, but there's a little bit of fluctuation and variability in these, but hopefully only 1% or 2%. But so we can see there's definitely a language effect here. Our highest throughput is provided by Go. Now what you can do when you run a test is you can monitor the cost using the Google App Engine dashboard. And it tells us for each test the exact amount of cost in terms of instance hours. So an instance is what's loaded to execute requests, and as GAE scales up, it loads more instances, and that's what it then charges you, as we said earlier, based on 15-minute intervals. So each test has a particular cost. What we did was we calculated the average cost for each test. So here, see, interesting, 20 instance hours. Go is actually, I think it's about 17 if you look in the actual data. So it's using less instance hours, i.e. less cost, and providing higher performance from the previous chart. Java, the other three, if you remember, were pretty similar performance-wise. There was a little bit of difference, but nothing too significant, all around 8,000, 9,000 requests a second. But Java's cheaper because it's only using roughly 25 instance hours, to execute a test, whereas Node is close to 40 and Python's over 50. So Python's roughly double the cost of a Java test and about 3 times the cost of Go. So this enables us to calculate a price performance ratio. So what is our mean throughput for every dollar that we spend? So here you can see that for this application, every dollar we spend, we're getting about over 10,000 requests a second for Go. For Python, we're only getting 2,500. Node and Java, it's 4 to 6,000. So not only is Go the fastest language implementation, but it's also the cheapest. So this is a pretty compelling argument for using Golang on Google App Engine. Java's pretty good too. Certainly its performance is comparable to the other languages, but it works out at quite a lot cheaper and hence provides you a better price performance ratio. So something as simple as choosing the programming language that you write your application in and deploy on Google App Engine, and I assume on other platforms that provide similar functionality, can provide you with very variable cost and performance. So this is an area where choosing wisely is a great idea. Next, we decided to experiment with the auto-scaling parameters that you can set in app.yaml. Here's the default settings of the 5 major ones that you get if you don't provide any values within your app.yaml configuration. So target CPU utilization is 0.6, 60%. Maximum concurrent requests is 10. By default, you get 6 because the target throughput utilization is 0.6. And the pending latencies are both 30 milliseconds. So obviously, if you vary these, there's a lot of interdependencies. And if you vary one or more, then you can end up with a very large number of tests that you need to execute to explore the variation that the parameters give you in performance and cost. So we limit. So for this particular experiment, we were just interested in varying 2 of the parameters in app.yaml. Basically, the CPU utilization and the max concurrent requests. Remember, CPU utilization by default is 60 and max concurrent requests is 10. So this is what you get by default. We've then varied for each test we ran with CPU utilization of 60. We varied max concurrent requests from 10 to 35 to 65 and to 90. So that gave us 4 test configurations. We then changed the default CPU value from 60 to 70. And we ran the same amount of tests, again 4 different configurations. And finally, we changed the CPU utilization setting to 80%, and we ran the same 4 tests. So we ended up with basically an experimental study design. We only used the Go server. It was the fastest of our 4 language implementations, so it was hopefully going to provide us with the best throughput and enable us to do more tests more quickly, because it was actually just executing quicker and cheaper, so we would use less of our budget when we didn't have an infinite budget for performing these experiments. So lots of tests. Each test was run multiple times, 5 times I believe, if I remember correctly, and the results averaged in terms of throughput and latencies, etc. And there's the detailed results are available. So what does it tell us? To explore this kind of experimental study, you can use response surfaces. So here we're plotting a response surface which shows the different points in our design space. So here we have the performance achieved with max concurrent requests of 10 and CPU of 60. Over here we have the performance plotted of CPU of 80 and max concurrent requests of 90. So here you can see the different points and how the response surface illustrates how the performance varies. So over here we're actually getting roughly the best performance. Over here we're seeing lower performance than we did up here. So we can see how the variation of the parameters affects the overall test throughput. If we just plot peak phase throughputs, this was the maximum throughput achieved during the peak phase, we see quite a lot of difference. So again, you can see the peak values of around 8,000 requests a second up here. So that was achieved with a maximum concurrent requests of 10 and a CPU value of 80%. So that's interesting. Whereas if you have the default setting, max concurrent requests at 10 and CPU is 60, you're getting some of the lowest performance. So you can see how the variation of the peak phase throughput is quite stark based on these parameter values. Of course, we can then compare the costs, the number of instance hours for each test. So here we see, and this is probably not totally unintuitive, that the highest costs are when we have the lowest number of concurrent requests allowed to execute within an instance. And as we allow an instance to execute up to 90 concurrent requests, then we see our costs falling. But as we saw earlier, that doesn't always play through in terms of the performance that we see. So these response charts show, response surfaces show how the variation in the parameters in the app.yaml really affect the throughput that you achieve and the costs that you incur. And we can also plot a price performance ratio here, just as we did with the languages. And again, not surprisingly, as the number of requests we allow an instance to execute, we're executing less instances, we're loading less instances to handle our load. So our price performance ratio is much higher than when we only allow 10 requests to be handled by each instance, or in fact 6 requests to be handled by each instance. So let's do some detailed comparisons based on real numbers. The response services are really interesting because they show the overall shape of the experimental space, but the numbers are really revealing when you actually compare them directly. So here you see the values, the throughput mean for the test. So here was 60 CPU of 60% and maximum concurrent requests of 10. We got a average throughput of 6,006, whereas for another one, CPU 80%, max concurrent request 90, we're getting about 5,600. So 400 requests a second variation there, from close to the highest to close to the lowest. And the table at the bottom shows the same values for each test, but based on instance hours. So this is cost. So cost is good. Cost is less is good. So again, we can see our default settings, we're incurring about 11 instance hours, whereas when we have CPU utilization set at 80 and 90 requests allowed on each instance, then we're seeing almost half the costs. And remember, for those two particular experiments, we saw only a variation of about 400 requests per second, so less than 10%. So it says here, higher performance is possible at 20% cheaper than the default settings. What does that mean? Well, that's our default setting, and we achieved 6,006 requests per second on average. This is our highest performance that we see within all the tests. It's not a great deal higher, small percentage, but it's definitely higher. Let's compare the costs of those two. Well, the first one cost us 11 instance hours. The second one cost us only 9. So we're actually achieving higher performance marginally at roughly 20% less cost. So just by adjusting these values, we can get better price performance ratio. And 20% doesn't sound a lot, but if you're incurring $100,000 a day of costs on the default, saving 20% would make your boss really, really happy. So that's interesting. What about we can achieve 96% of the default configuration performance at 54% of the default configuration costs? Where do we get that from? Well, here's our default configuration cost. It's 11 instance hours. Our lowest instance hour cost was achieved here, actually these two, but this one's more interesting. So this is when we had CPU set at 70% utilization and max concurrent requests at 90. Let's look at the performance that these two tests give us. This one's good old 6006, we've seen that one before. This one's almost 5800. So that is actually 96% of our performance of the default, but we're only paying 54% of the costs. So if 5,793 requests per second average throughput was sufficient for your application purposes, you can save almost 50% cost just by varying these parameters from the default setting. So yeah, maybe it's not surprising that the default settings don't provide you with the cheapest performance. Google's a business, remember? So this is interesting. It shows that you really need to plan wisely when you use these application platforms. Otherwise, you may be in for some surprises. For comparison purposes, let's take a quick look at the Amazon Web Services Lambda platform. So Lambda conceptually is very similar to what we just described with Google App Engine. You deploy your code as a server, which is a stateless Lambda function. They're triggered. Lambda functions are triggered by the HTTP requests arriving at the endpoint, or by an event on some AWS service, such as an S3 bucket being modified, or a DynamoDB table being triggered, an update on a DynamoDB table, or an SQSQ message arriving, etc. There's various ways of doing it on AWS. Unlike GAE, instead of being charged per 15-minute instance utilization, charges are actually based on a very fine-grained 100 millisecond metering interval. So you pay for whole numbers of 100 milliseconds that your service is executing for. And just like GAE, Lambda is responsible for scaling your application automatically. And we'll see how it does that a little bit later. It's subtly different. Here's an example Lambda function. It's a really simple one. It just takes a parameter of an integer, a count, and also when the function is called, Lambda adds a context, which defines the runtime context for a particular function. It has a number of properties that you can use. Here we're using a logger property that we can get from our context. And we get the logger and we log that we've received a request. And this sort of thing that you would do if you're doing monitoring or debugging, etc. And then the function returns a string, so we just return a string value that represents the myCount value that we were passed. And so AWS will then marshal this result back to the client over HTTP. Simple. There's also an API gateway which AWS provide you with. We talked about API gateways earlier. Basically, it just enables you to expose your Lambda functions as HTTP endpoints and then map the request from the API gateway to your actual Lambda functions that you've deployed. And remember, these could potentially be in different data centers around the world. So as I said, no specific frameworks are required for the languages that AWS supports. It supports all the main languages you'd expect. When you deploy your Lambda function, you basically specify the amount of memory that you want your function to have. And based on the amount of memory that you specify, AWS allocates proportional CPU power and network bandwidth and disk I/O, and of course charges. And you can see here the table that shows the choices of memory and the basic costs that are incurred as you choose the amount of memory your function requires. So that's certainly an experimental parameter that you could play with, just as we did with Google App Engine, to see whether having additional memory helps your performance and is worth it in terms of cost. How does scaling work? So very much like GAE, when the first request arrives for a deployed Lambda function, the first request loads the function and runs the handler method. So it just runs the method. When the same function instance is called again, that resident instance can be reused after the first requests have finished. So once it's deployed, you don't pay the startup costs. As more requests arrive, Lambda basically will route them to available instances that have been deployed that are resident within the Lambda platform. And if there aren't any available ones, then it will create new instances to run the increasing number of requests. If there's a burst of instances, such as suddenly, like we saw when we did our performance testing, we grew from 512 clients to 1,024, and this doubled the throughput that GAE was able to provide. If a burst arrives, Lambda actually throttles the amount of instances it will load, and it varies on the region, the data center where your Lambda service is running. So it will throttle it to increase by either 500 requests a second or up to 3,000. And I assume this is based on the sort of underlying hardware availability that each data center has to run Lambda functions. So it ensures that it can be shared across multiple customers, and not one customer can suddenly hog all of the Lambda resources in a particular region. Once you've done that initial scaling, you can scale by up to 500 instances per minute after the initial burst. So you can keep growing, but your first burst is throttled to some known value. You can also reserve the amount of instances that you can run up to, basically putting a cap on the function. And this provides, just like the maximum instances in GAE, a known cost for your service, so you won't get any surprises at the end of the month. So in summary, serverless platforms are available on all of the major cloud providers. They're there to make the deployment and management of your services frictionless, admin free, as it says on the slide here, basically to reduce the complexity of administering your services. We've looked at examples from Google App Engine and briefly from AWS Lambda. Azure has similar things, Azure Functions, and they all behave similarly but differently. They're all conceptually the same, but the details are different in terms of how you configure them and how you pay for the services. So it's important to understand these differences if you're going to choose between one of these, and once you're deploying on a particular platform, it's important to understand how the configuration settings will affect both your performance, your scalability, and the costs that you incur. As usual, the devil is in the detail. Thank you.